The paper is InftyThink plus Effective and Efficient Infinite Horizon Reasoning via Reinforcement Learning by Yuchen Yan and the team at Zhejiang University and Ant Group. Okay, here is the 1-minute summary. So we're looking at a framework that basically challenges this whole obsession with gigantic context windows. Instead of one huge memory-eating chain of thought that runs into that, quadratic cost of attention, InftyThink plus chops reasoning into little segments. It summarizes the last step before it moves to the next one, which keeps the context window bounded. The big innovation here is using an end-to-end reinforcement learning framework. So it teaches the model when to summarize and what to keep instead of just copying human formats through supervised learning. They evaluated it on DeepSeek R1 Distill Quen 1.5b, and it improved accuracy by 21% on the AMI24 benchmark. It also outperformed standard long chain of thought RL by 9%, and this is the big one. It cut inference latency by almost 23%. It's essentially infinite reasoning without the infinite memory cost.
That's a really tight summary of what might be one of the most important efficiency papers we've seen in a while.
Well, I'm trying to optimize my own token output here. But seriously, welcome back to AI Paper Podcasts. We had to tear into this one because it feels like a direct shot at the spec sheet wars.
Well, absolutely.
With Gemini 1.5 Pro, the latest GPTs, everyone's just bragging about 1 million, 2 million, 10 million token windows.
Exactly. The industry right now is trying to solve reasoning by brute forcing memory. The whole logic is if we want the model to think longer, well, just give it a bigger scratch pad.
Which works, until it doesn't.
Right. It hits 3 main walls. First is the quadratic complexity of self-attention. For any engineers listening, you know this. Doubling your sequence length doesn't double the cost.
It quadruples it.
It quadruples it. The KV caches explode.
Explodes.
Then you have the hardware limit. I mean, even with H100s, you eventually just run out of VRAM. And third, and this is maybe the most frustrating one for researchers, is the lost in the middle phenomenon. Just because you can fit 100,000 tokens in context doesn't mean the model is paying any real attention to token number 5,000.
Yeah, the signal-to-noise ratio just dies.
It tanks.
So InftyThink Plus comes along and says, hey, let's stop trying to remember everything perfectly. Let's learn to take notes.
Let's learn to manage state. That's the real paradigm shift. It's moving from just this linear pileup of tokens to a proper iterative process.
Okay, let's visualize this. In a normal chain of thought, if I graph memory usage over time, it's just a straight line going up and up and up until it hits that ceiling.
Correct. With InftyThink plus OBIS, it's a sawtooth pattern. So you have the query, then it generates iteration one, say, a paragraph of reasoning. Then the model pauses.
And it summarizes that paragraph.
It generates a summary of iteration 1. And here's the trick. For iteration 2, it throws away the full text of iteration 1.
It just drops it.
It drops the raw tokens. The input for the next step is just the original query plus the summary of iteration 1. It generates new reasoning, summarizes that, and then from iteration 3, it drops the summary of 1 and just keeps summary 2.
So the context window stays flat. It never grows beyond query plus 1 summary plus the current thought.
Exactly. It bounds the memory complexity. You could, in theory, reason for 1 million steps, an infinite horizon, and your VRAM usage would stay constant.
Okay, but we've seen ideas like this before, right? I remember papers like DelaThink or Markovian Thinker. They tried this. Why didn't they take off?
Because they were mostly relying on heuristics, like just cutting off context. Or, and this is the crucial part, they use supervised fine-tuning, SFT, to teach the summarization.
Okay, let's drill into that because SFT seems like the logical way to do it. You take a long reasoning chain, you get GPT-4 to write nice summaries for it, and then you train a smaller model to copy those summaries. Why does that fail here?
Because SFT teaches the format, but it doesn't teach the utility. It teaches the model to write something that looks like a good summary to a human. First I did X, then I calculated Y.
Right.
But it doesn't teach the model to preserve the specific, messy little details that might be critical for a calculation 10 steps later.
Okay. So human-readable summary might smooth over some weird floating point number because it looks like noise, but that number is the key to the whole problem.
That's the perfect example. SFT creates a summary writer. InftyThink Plus uses RL to create a state manager. And the only way to get there is to let the model try, fail, and learn what to keep based on whether it actually solved the problem in the end.
Okay, so let's get into the training recipe. Because it's not as simple as just throw some PPO at it, right? They've got a whole pipeline.
They do. It starts with what they call a cold start stage. You can't just start with pure RL because the model doesn't even know it's supposed to summarize. It would just, ramble on forever.
So they do use SFT at the beginning.
Yes, but only to bootstrap the format. They take standard chain of thought, data query, reasoning, conclusion. They chop the reasoning into segments, and then they use a helper model, like Quinn, to generate and insert summaries between those chunks.
So they're basically creating synthetic data that looks like this reason-summarize-reason structure.
Exactly. They train the base model on that just so it learns the rhythm.
Okay, after I think for a bit, I output a special token and write a little recap. That's all stage 1 is for.
The mimicry stage.
The mimicry stage. Stage 2 is where the magic happens. They switch to reinforcement learning. And they specifically use GRPO group relative policy optimization.
Which is what DeepSeek used for R1, if I remember correctly.
Very similar flavor, yeah. It's known to be more stable than PPO for these complex reasoning tasks. But the real innovation here is the reward function. It's a multiplicative.
Right, so it's reward equals task reward times efficiency reward.
Yes, and that multiplication is so important. The task reward is binary. Did you get the right answer? 1 or 0. The efficiency reward is a curve that penalizes you for taking too many iterative steps.
But because you multiply them, if you get the answer wrong, the task reward is 0, so the entire reward is 0.
Precisely. You get absolutely no credit for being fast and wrong. You only get points for being right, and you get more points for being right and fast.
Okay, but what about the credit assignment problem? That's like the classic RL nightmare. If I write a summary in step 1, and that summary has some crucial variable that lets me solve the problem in step 10, how does the algorithm know that step 1 deserves a reward?
Yeah, that's where trajectory level optimization comes in. They treat the entire chain, all the reasoning, all the summaries as one single episode. If that final answer is correct, the positive reward signal, the advantage, propagates back to every single token in that whole chain.
So the model basically learns, hey, that time I kept that weird-looking vector in the summary back in step 1, I got a cookie at the end. I should probably do that again.
That's it exactly. It learns to connect the content of the summary with the eventual success of the task.
Yeah.
It's not learning to write pretty English prose. It's learning to encode a useful state vector.
I saw a technical detail in there that caught my eye. Something called ice pop. Is that just a cool name or is it actually important?
Oh, it's doing something super critical for stability. It's a bit of a weird acronym, but it solves the mismatch between the inference engine and the training engine.
Because for inference, for generating the rollouts, they're probably using something fast like VLLM.
Exactly. But for the backward pass, for the actual training, they're using PyTorch or something similar. And you can get these tiny numerical deviations, little floating point errors between the two. In deep RL, those tiny errors can make the KL divergence spike and just completely collapse your training run.
So the model thinks it's drifting off policy, but really it's just a rounding error.
Right. IcePop is a clever trick that masks the gradients for tokens where that probability drift is too high. It just assumes it's noise from the engine mismatch and ignores it. It's what keeps the whole thing stable.
Got it. Okay, so before the results, let's talk hyperparameters. They mentioned phi and eta.
Yeah, those are the main knobs they can turn. Phi is the maximum number of iterations. You can think of that as controlling the depth of thought. How many rounds can it think for?
Okay.
And eta is the context window size for each individual segment. So that controls the width of its thought at any given moment.
And I'm guessing there's a trade-off there.
A big one. They found that increasing phi, so letting the model think for more rounds, really boosts accuracy. That makes sense. But they have to keep eta, the window size, pretty tight. If the window's too big, the model gets lazy. It doesn't learn to compress efficiently.
So constraint breeds efficient compression.
Exactly that.
All right, let's hit the benchmarks. They tested this on a 1.5 billion parameter model. What happened on AME24?
AME24 is a really hard math benchmark. The base model scores around 29%. With InftyThink plus C, it jumped to over 50%.
Wait, that's a 21% absolute improvement.
It's a massive jump. In the world of LLMs, a 2% improvement is a paper. 21% is like a generational leap.
And it beat the standard long-caught RL approach.
By about 9%. But the real headline for me isn't just the accuracy, it's the latency. Normally, when you use RL to make a model smarter, it learns to think for a very, very long time. It gets slower.
Right, smarter equals slower. That's usually the rule.
InftyThink Plus breaks that rule. On a similar benchmark, AME25, it improved accuracy while reducing inference latency by 32.8% compared to the vanilla long context method.
That's huge. It's actually decoupling reasoning depth from the cost of inference.
Yes, because the context window never grows. That self-attention mechanism never hits the quadratic part of the curve. The model can think deeply without paying the wide tax.
And this wasn't just a math trip, was it? They checked if it generalizes.
They did. They ran it on GPQA, which is like graduate-level science questions, and on coding tasks. It showed solid gains there, too. And that's critical because it proves this whole iterative summarization thing isn't just a hack for algebra. It's a general reasoning architecture.
Okay, I want to pivot to what I think is the most mind-bending part of this paper. This really gets at the whole RL is a black box critique. They did an experiment where they tried to help the model.
Ah, the perfect summary experiment. Yeah, this is so fascinating.
Walk us through it.
Okay, so they have their InftyThink Plus model that's been trained with RL. During inference, they step in. Instead of letting the model write its own summary of the last step, they swap it out and inject a perfect summary written by a really good external model, QuinInstruct.
And the logic there is better summary in, better performance out, right?
That's what you'd think.
Yeah.
And for the SFT, the supervised version of the model, that was true. The better summary helped. But for the RL version,
It hurt performance.
it hurt performance. The perfect human-readable summary made the model dumber.
That is so counterintuitive. Why would a clearer summary make it fail?
Because the RL model wasn't writing summaries for us. It wasn't optimizing for readability or for making sense to a human. It was optimizing for pure information transfer to its future self.
It developed its own shorthand.
It developed a proprietary compression format. It might be keeping a specific activation or a weird turn of phrase that looks like total gibberish to us, but to the model, that exact sequence of tokens triggers the right computational state for the next step.
So this is the information bottleneck theory in action.
Exactly. RL is optimizing that trade-off between compression for getting all the noise and informativeness keeping just the signal. A generic human-style summary throws away things that look like noise to us, but are actually crucial signal to the model. We were trying to help, but we were just stripping out the load-bearing data.
Wow. This feels like a turning point. We always assume that chain of thought is the answer for interpretability. We can just read the logs and see why the AI did what it did.
This paper suggests that window might be closing.
Right. Because if the reasoning is broken up by these compressed summaries, and those summaries are just dense blocks of, alien shorthand.
Then you're back to a black box.
Yeah.
You can read the words, but you can't understand the state. The summary is an encrypted cipher, and only the model itself holds the key.
It's like the model is taking notes in a language it invented 5 minutes ago for this one specific problem.
Effectively, yes. And we have to ask, are we okay with that trade-off? We're trading human interpretability for machine efficiency and, infinite reasoning.
For an autonomous agent that needs to run for a week to debug a whole code base, maybe we don't care. You can't keep a week's worth of logs in active memory anyway. You need some kind of rolling state.
Exactly. If you want an AI to write a novel or design an entire operating system, it can't remember every single keystroke. It needs to remember the plot or the system architecture. InftyThink Plus really proves that RL might be the only way to teach that kind of strategic forgetting.
Because SFT can't do it. We as humans don't actually know what the important bits are to remember for step 50.
We don't know the future state of the problem. Only the model, through thousands and thousands of trial and error simulations, can figure out what really matters.
So, wrapping up, what's the big takeaway here for the researchers and engineers listening?
I'd say stop obsessing over the context window size on the spec sheet. It's a brute force metric. The real frontier is state management. How do we compress, essentially, infinite reasoning into finite memory?
And the answer seems to be cold start with SFT to get the format, then use RL to learn the actual compression strategy, and maybe accept that the resulting thoughts might not be meant for human eyes.
That really seems to be the trade-off we're heading for.
It's a fascinating future, a little unsettling. Infinite reasoning, super efficient execution, but maybe a bit more opaque than we were hoping for.
Efficient, effective, and encrypted by its own logic.
We'll definitely check out the paper InftyThink Plus 2 for all the architectural details, especially that IcePop implementation if you're building out your own training stack. Thanks for listening to AI Paper Podcasts.
Thanks for having me.